Okay, guys, let's talk about the binomial probability distribution. The binomial probability distribution is part of discrete probability. And this video is going to be the first in a series explaining the binomial probability distribution, because I think it's going to take more than one video to really go through it comfortably. So this will be the first one. And by the way, if you're not clear, you don't remember well what's the difference between a discrete probability distribution and a continuous one, go ahead and let me know in the comments, and I will hopefully clarify that for you. Okay, binomial probability. Let's imagine a scenario just to set this up, to be able to make it clear when we need it. By this time, most of us have gotten pretty familiar with probability questions involving a coin, especially when you're flipping a fair coin. I used a coin in my geometric probability distribution video. In this case, I'm proposing that we think about a fair coin. So this is the coin where the probability of heads is 1/2 and the probability of tails is 1/2. If I asked you, hey, what's the probability that we should flip a coin like this 3 times and get 2 heads? Well, we could probably figure that out. I'm going to write out the sample space for this sort of scenario, and then we'll take a look at it. Okay, so there's our sample space. So what we want to do is figure out what's the probability that we would get 2 heads in 3 flips. To do that, we can rely on a shortcut. Now we know that this coin is a fair coin, meaning the probability distribution between heads and tails is symmetrical. Both outcomes have the same probability. They are even. So what we can do is count the outcomes. There's 8 of them. I'm going to put that in our sample space. And then count the ones that we want, which are these 3, and put that in the top. And then we're done. This approach is very easy and elegant, but it breaks down sometimes. 2 circumstances where it breaks down are: what happens if we have a coin that is not fair? If the coin's probability distribution was not symmetrical, we could not count outcomes and put that in the denominator for our probability fraction. It wouldn't work. Also, what would happen if we were thinking not about 3 flips or 4 flips, let's say 10 flips? Now, you could probably write out that sample space given enough time, and you could probably calculate all those probabilities, but it's really difficult and it would be really time consuming, and we need a better way to do it. So let me go ahead and fill in some different probabilities. I'm going to reuse a probability distribution that we used in my geometric probability distribution video. Let's imagine that we have a coin where the probability of heads is 2/3, and that would make the probability of tails 1/3. And I want to say, out of 10 flips, what's the probability that we would get exactly 3 heads? Now that's kind of a difficult problem. We're going to have to tackle a number of issues to be able to do that. The first thing to do is to take a look back at one of the outcomes we had in the previous part of the question and take a look at it carefully. Here was the subset of the sample space for when we were doing 3 flips. Here's the subset of that sample space that had 2 heads. Now, if you calculated those probabilities, it might not be a bad idea for you to go back and take a look at that carefully. You're going to realize that the elements of each of these 3 individual parts of the sample space are the same. There's 2 heads in each one, leaving 1 tail in each one. So I already know that if we're talking about 10 flips and I'm looking specifically for the probability of 3 heads, that I'm going to automatically get 3 heads, and that means that I'm going to get tails 7 times, because we're making it a requirement to begin with that we're thinking about 10 flips. So what I can do is I can look ahead and know that if I were going to calculate all of those individually, I'd be incorporating into each one of those individual calculations, each sequence of 10 flips that would incorporate 3 heads and 7 tails. They would have the same elements. They would have the probability of heads 3 times. So I'm going to raise this to the 3rd power. And they would have the probability of tails, and I'm going to multiply them the remaining times, 7 times. And that's going to characterize each one of the calculations that I make. But that's not going to give me the whole answer, because out of a sequence of 10 flips, there's got to be a way to figure out all the different ways that we can insert in that sequence of 10 the 3 heads. I want you to imagine this. Here's one way we could get 3 heads in 10 flips. Okay, if I haven't made a mistake, that's 10 flips. But what if we had heads, tails, heads, heads, tails, tails, tails till the end? And then what about heads, tails, tails, heads, tails, heads, tails, 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 all the way to the end? We have to have a way to figure out how many different ways there are for us to get a sequence in which we have 10 flips that incorporates 3 and exactly 3 heads. And the way that we are going to do that is to use something called combinatorics. And that's going to be the subject of the next video.